right. Let's do this one last time. I can even close the tracing tool. All right. So we want to do graphs today. Let's do exactly that. So we want to prep for task 8. That's what this lecture is all about, getting you through task 8. We don't have any memory diagrams on graphs, so it really is all about the programming task. This is the way you're being assessed on graphs. And we want to write this degrees of separation class with the degrees of separation method, which is going to take an array list of movies and 2 cast members and return the degrees of separation between those 2 cast members, which is the number of movies that you have to traverse to get from one cast member to another. And I have extra explanation in here explaining the flavor of the assignment. What it's going to end up boiling down to is distance in a graph. So we'll define all the terms and figure out how to do that using breadth first search. That's what we want to do today. And this is one of the only deviations from my from the 11 a.m. I will use some slides today. I'll pretty much go through all of this second set of slides. I'm not going to touch this last one. This is a memory diagram, which we're not going to do because there's no quiz for this. We're going to do more live coding for that instead. And I'll do a few slides from this, mostly the intro slides, just to set up what graphs are. This would be a difficult one to do in the code, so I do want to do a couple of slides introducing graphs, mainly this slide, given the background of all the data structures. This overview would be tough to do without the visuals. So we've learned a bunch of data structures. The first question is, like, why are we even learning graphs? Why do we need another data structure? We already have a whole mess of them. Do we really need another one? So let's just review which ones we have and why they're not going to do the job for us here. So we have our 2 sequential data structures. This semester it was our array list and our linked list. These are sequential, meaning that the order matters. If I insert the values 5, 20, and 3 in that order, I expect them to stay in that order, either by indices or by linking nodes together. That order does matter to me. Then when order didn't matter and we just wanted to store associations, I want to associate some key with some value. We used our key value stores, hash map this semester, dictionary in 115. To associate those keys with the values. Order didn't matter, so the order that we insert these in is irrelevant. It's just going to store these values stored at those keys. And we had one nonlinear data structure in a tree, specifically binary trees that we saw this semester, where each node refers to 2 other nodes, and we can have this branching structure, which allowed us to do different things. We did binary search trees, which gave us some log n efficiency as long as the tree was balanced. So we had a more efficient data structure, but we could also represent more information this way. We could do decision trees. I always do my 20 questions example where we can have a node that decides which way to go, and then either left or right is going to eliminate half of the nodes remaining in the tree, which is a very powerful, gives us that log n math out of the equation. And then we're going to get data like this. So we have subways in New York City, so we have stations connected by lines. We have road maps, so we have intersections connected by roads. Or we have this example where we have locations on the early days of the internet, back when it was ARPANET still, connected by cables. And then these locations are all the foundation of the internet. They're very, very early days of the internet. Which is the example... I guess not really. Oh yeah, we will, because I'll go to the next set of slides. This is the example we'll see when we come back to the slides, but we'll do quite a bit in the code before we get back to that one. But how do we represent data like this, where we have a different type of different type of data that isn't really going to fit in any of our data structures? And this data is nonlinear, so the only option that we have out of the data structures that we know is going to be trees. And of course, the answer is going to be graphs because that's the name of the lecture. But the only option other than that would be trees. So let's try to represent this as a tree. So let's start at UCLA, call that the root of the tree, and then all the child nodes are going to be all of the locations connected to UCLA. And then when we go to Stanford, all the connections here, SRI and UCLA, are going to be Montenegro, are going to be the child nodes of Stanford, which is UCLA SRI. And we have issues here. We have duplicate nodes. UCLA is in here twice. SRI is in here twice. We're just going to have strong issues if we try to create a tree representing this information. It's not going to work. So we're going to introduce a graph, which is very similar to a tree, except when we have this situation here, instead of creating new nodes, we're going to create references to the nodes that already exist. That's what we want to do. So UCLA to Stanford, Stanford sees UCLA. We already have that connection. Then Stanford's going to connect to the existing SRI instead of creating a new SRI node. And that's the big difference here. That's what we're. That's how we're going to represent our. Not how we're going to represent them, but that is now a graph, which is very similar to a tree, except it can have cycles. So this is a cycle. If we can travel from one node back to itself, that's a cycle. That we cannot have these in trees. If we had these in trees, our traversal algorithms would all get stuck in infinite recursion and blow up the stack and Stack Overflow. So we have this situation in graphs. This is allowed in graphs. We can have cycles. And we can start representing this data that naturally has cycles in it. But we're going to have to come up with new algorithms, new ways of representing this data, just new ways of doing everything with this new data structure. And I think that's all I want to do in the slides, at least for now. I think I'm even going to skip some of my explanation in the slides that I usually do in the slides. But I think that's all I want to talk about from that slide deck. That's what a graph is. Now, since it's the 11 a.m. lecture, let's build this. So let's talk about how to represent this in our code. So let's create a graph class and talk about how we're going to represent that information. And there's a few different ways. When you do 191, 250, 331, they're going to talk about two different ways to represent graphs. There's an adjacency matrix. So first of all, this is going to be a graph of, let me get my notation consistent. I used capital N here. It's going to be a graph of something. Adjacency. And we can represent our information in a few different ways. Adjacency matrix is something we're not going to use this semester, but if we were, no, I'm not even going to set up the whole thing, but it's similar to this. Array list of array lists of, I like to just use booleans whenever I'm using one of these, of booleans. Whoa, not the primitive. Boolean. Oh my goodness. Adjacency matrix. And what this is saying is that for each pair of nodes, which we'd have to give the nodes indices, and for each index, each pair of nodes, we're going to have a Boolean which tracks whether there's a connection or not between those two nodes in the graph. We're not going to do this, so I'm not going to bother building this out anymore. But when you take those other classes, you are going to see adjacency matrix, but in 116, it's not going to be relevant for us. So I'm not going to mess with it anymore. What we are going to see is an adjacency list. That's the one we're going to use, so that's what I'll talk about the rest of the time. The rest of the lecture today that we're talking about graphs. So instead of the way we did linked lists and trees, where we had a node class and then we had node objects, and the node objects had references to other nodes, I don't think I'm going to put anything there. We're actually going to do that a little differently in graphs. So with graphs, we're going to store one data structure which contains all the information we need, and that data structure is going to be what we call an array list, but it's how we're going to represent our graph. And that's going to be a hash map of nodes of some type n to an array list of nodes. This is going to be our adjacency list as a data structure. I don't know, I'll do it the same way I have it in the other code. This is going to be initialized to an empty hash map. So graph, definitely not that. Graph this dot adjacency list equals new hash map. And this is how we're going to represent our nodes and edges. I didn't define edge yet. Node is what we are used to seeing. It's the actual data in the graph. And then an edge exists if there is a connection between those two nodes. And unlike linked lists and trees, where those edges had a clear direction, you had a parent node referring to the child nodes, you had a node referring to a next node. With a graph, at least the graphs that we're going to do in 116, the graphs are going to be what we call bidirectional, meaning each edge can be traveled in both directions. So if there's two nodes that are connected by an edge, there's no node and next node relationship. There's no parent-child node relationship. Those two nodes, we just say that they are neighboring nodes, and neither one of them is special. There's also no special node in the graph, like there was the head of the linked list, there was the root of the tree. With a graph, they're all just in one big pool. They're all just the keys of this hash map. So this hash map is going to store all of the nodes in the graph as keys. And for each node, it's going to know an array list of all of its neighboring nodes. So the adjacency list for each node, we're going to store effectively all of the edges connected to that node. So a list of all of the neighbors of that node. And that's going to capture all of the information of our graph. So the hash map is nodes to an an array list of all of its neighboring nodes. And there's one public method that we're going to want for this. Actually, two. Let me get the other one out of the way lest I forget. One is going to be the getter for the adjacency list, something that'll be very useful for your homework. We want to get adjacency list, return this dot adjacency list, cool. And the other one is going to be to add an edge. And I'm going to call this add bidirectional edge just to be consistent with the code in the other graph class. Add bidirectional edge, which returns void. And this is going to take two nodes. And add these nodes into that adjacency list. And I'm actually going to write another helper method because our public facing, we're only going to have a way to add edges, but I do need to add nodes here. I'm going to make this private, but let's just think about what we need to do to add a node. And for this, I'm going to lazily initialize, which I used that term a bit this semester. I don't know if I fully defined it. That means we're going to initialize at the last possible moment. So we're not pre-initializing any of our data structures. We're only going to initialize things as needed. And we want to ask ourselves one question. Have I seen this node before? This should seem very similar to task 6, where you're saying, have I seen this song before? Should I create a new song, or should I just add this rating? Have I seen this movie before? Should I create a new movie, or just add this rating to the existing movie? We want to do the same thing here with our adjacency list. Have I seen this node before? Because if I haven't, if the adjacency list does not contain this as a key, so this means I have not seen this node before. So I'm setting up this method in a way that I can just call it, even if I'm not trying to add a brand new node, I'm just going to call add node and let it handle the check whether I've seen the node or not before. I'm going to add a node. So have I seen this node before? If not, I want to initialize it. this .adjacency list.put. I'm going to put a key value pair into my hash map of the node, this new node that I'm seeing for the first time. I'm going to put it into my hash map with a new array list because I haven't seen any neighbors of this node yet. It's just a node. I don't know anything else about it. I'm just going to lazily initialize its adjacency list to an empty array list. Then when I add my bidirectional edge, I want to set this up in a way where I can just add edges and not have to worry about anything else. So this dot add node, when I add an edge, I'm going to call add node on node 1, add node on node 2. So if I've seen these nodes before, nothing's going to happen. This condition will be false and the method does nothing. But if it's the first time I've seen one or both of these nodes, it's going to initialize my adjacency list to make sure I don't get any errors on the next line when I actually add these edges into my adjacency list. So this dot adjacency list, I want to get the array list at one of the nodes and then add to that array list the other node. And vice versa. This is a bidirectional edge, so I have to do this in both directions. So node 1 and node 2 both need to know that the other one is a neighbor of it. Then I'm not going to do any formal testing today. I'm not writing any test cases, but I will go to the old-fashioned main methods just so we can at least see this code in action. So let's use one of these, use this code to generate a graph. I think that's where this code becomes a lot more clear. I'm going to do a graph of strings, and in your homework, in your task 8, you also, morning Dave, did I miss that? What time is it? Yeah, I did miss that, sorry. Is going to be a graph of strings on your task 8 as well. Missed an equal sign. Graph of strings, and then let's call graph dot add bidirectional edge and start adding some connections. I think I'll cheat just a little bit here and take some of the example from the lecture, UCLA to Stanford. Oh, I did all capital here. Stanford, and start adding edges into this graph. So I'm capturing this information that there are connections. Not going to do the whole graph, just because you'd have to sit here and watch me do this whole graph. UCSB. Rand, Stanford, SRI. Then let's just add a line so I have a spot for a breakpoint. Let's take a look at what we get when we create this graph. So I'm adding 5 different edges into my graph. So I should have this information of these 5 edges inserted into my graph. So let's take a look at our graph. Our adjacency list is size 5. So we expect 5 nodes. We have UCLA, Stanford, SRI, UCSB, and Rand. That's 5 nodes. So I should expect those as my 5 keys in my graph. So my adjacency list, for each one of these nodes, I'm going to have a list of all the neighbors of the node. So for Rand, our first one here, we only added 1 edge with Rand, so I expect its adjacency list to just be UCLA. That's the only node that you can get to from Rand, since we only added these 5 edges. That is exactly what we get. Let me resize things a little bit here. So that's exactly what we get. Rand maps to an array list with just the value UCLA. But if we go to UCLA, we should see all 4 of these edges: Stanford, SRI, UCSB, and Rand. We see all 4 of those neighbors of UCLA. Those are all neighbors of UCLA, so we can see all 4 of those nodes in there. And when we're looking at this adjacency list, notice that every edge is in here twice. So we can go from UCLA to Rand, and we can go from Rand to UCLA. So both UCLA and Rand know about each other because they are both neighbors of each other, and that's why we do this line right, these two lines right here. We go to the adjacency list and tell both nodes, hey, add to your adjacency list, add to your array list, the other node. So since we added to both of them know that that is a neighbor. And what that's doing is capturing this bidirectional nature of our graph, the fact that each node can be traversed in either direction. Technically, we actually do have two edges. Since it's bidirectional edges, there's an edge going from node 1 to node 2 and from node 2 to node 1. So it's two different directional edges to represent a bidirectional edge. And directional graphs, that's something, again, 191, 250, 331. They'll talk all about directional graphs. We're not. Just not part of 116. So we're not going to talk about them. And then we can look at the rest of this. UCSB has UCLA as a neighbor. SRI, we expect Stanford and UCLA. In the reverse order, though. UCLA and Stanford. And then Stanford, UCLA, and SRI. UCLA, and SRI. So this is how we're representing our graph. It's a hash map of nodes to array lists of nodes to capture all of the node information. That's just all the keys in this hash map. And all of the edges, which are the array lists. The array lists are capturing all of the edge information. So with that, you can have all of your information of your graph represented in this format, in this hash map of nodes to array lists of nodes. So really, it's a new data structure we're learning, but really it's a combination of two data structures that we've been using all semester, these hash maps and array lists. And this is part of why I'm not sad that we cut the memory diagram for this, because the memory diagram is all things that we've talked about in the first week of the course, array list and hash map. We could really give you the graph trace, the tracing quiz. We can give that to you at the end of week 1. You should be able to do that. So there's no new concept to learn when tracing a graph. It's all just a lot of hash map and array list application. Pretty complex applications, but that makes for a terrible quiz because it's just tedious without actually assessing new knowledge. There's no new concepts that I'm assessing there if we have that. So that's part of why there's no trace for graphs. If it were another node-based data structure like linked lists and graphs, what up, Arkash? And Arkash, oops, I put the R in the wrong spot. If it were another node-based data structure where we have references to objects on the heap, then it'd be more worth it to have a graph trace, but it isn't, so we don't. And if we look through this code, let's move our breakpoint up a little bit. Let's stop this one. We can see the rest of our code in action. So we're going to add this edge, UCLA and Stanford. Our graph is completely empty at the moment. We're going to add bidirectional edge. First, we're going to add UCLA as a node. We're going to check, does our adjacency list contain the key, this adjacency list, does it contain a key of UCLA? And no, it doesn't. It's a completely empty hash map. So we're going to initialize it. This is the first time we've seen UCLA. Let's initialize its adjacency list to a new array list. Now we have an adjacency list size 1, UCLA, mapped to an empty array list. That's what we wanted. Do the same thing for Stanford. We haven't seen Stanford yet, so we're going to initialize it. Now we have this adjacency list. We have two keys, UCLA and Stanford, both of size 0, and now we're going to tell each one of them that, hey, you just got yourself a new neighbor, and tell each other that they are neighbors of each other now. So we're going to get the adjacency list, this dot adjacency list dot get node 1. Node 1 is UCLA. Let me resize this. Is UCLA. So get the value at this key. The key is UCLA. The value is this array list at 947. And then at this array list, we're calling dot add node 2, which is Stanford. So we're going to add Stanford to this array list right here. So now that array list has Stanford in it, and now vice versa. Go to the this .adjacency list .get Stanford returns a reference to this array list here. Then we're going to call add node 1, which is UCLA. So we're going to get UCLA in this array list right here. So we initialized both nodes and then told each node that it has the other node as a neighbor. When we get to the next one, we're going to add UCLA. I'm not going to go through this whole thing, but we're going to call add node. This is the last part I want to talk about. Add node on node 1. It's UCLA. I mean, I'll go through the whole thing if you want me to, but it'll get so repetitive. I assume you don't want me to. And then now this conditional is false because our adjacency list already contains UCLA. And we want to be careful here because we don't want to overwrite this information we already have in here, the fact that UCLA has Stanford as a neighbor. So since we've already seen this node and we already have some information, we're just going to skip this. We're not going to initialize anything. It's already been initialized. Same thing with your song. If you already have a rating in your song object, you don't want to overwrite that rating. You want to preserve that information and just call add rating on that song instead of creating a new song object. Okay, so same concept, same idea as that. Which is a very important thing to know. It's part of why we do it in 116. Got to know it. So here's our graph class. That's it. Let's get rid of this print line. We really don't need that. This is our graph class. This is all you need from the graph class for your assignment, for your task 8. So we have an adjacency list, which is tracking all of the nodes and all of the neighbors of all the nodes. So it captures all the nodes and edges in the graph. A getter for the adjacency list, so you can actually mess around with the adjacency list in your homework code. Add bidirectional edge, which is going to add this edge that can go in both directions for a node. And a helper method to add node to initialize the adjacency list for that node if it's the first time we've seen the node. Professor, I'm still in high school. Let's just say I do complete a bachelor's degree in computer science in the future. How likely am I to be unemployed? It depends. Well, first of all, in 4+ years, everything could be completely different. It could be from the market. Right now, the market's kind of crappy. But in 4+ years, the market could recover and there could be tons of jobs again, or AI could take over and none of us could have jobs. It's really hard to tell. What I will say, though, is if you go to college and you really study and take everything seriously and work hard and actually learn everything that you're expected to learn, you're going to have a much better time in the job market. Those students very rarely have trouble. They can choose where they go. They got multiple companies trying to hire them because companies still, even with AI, they need people who understand code and can write code, debug code, maintain code. We're always going to need those people. I don't see AI getting to that level, at least not anytime soon. Maybe it will someday. But if you know how to do all that stuff, I mean, companies need you. They need you, and they're willing to pay a lot of money. If you're one of the students, like there are a lot of students who just like to use ChatGPT for everything. If you're one of those students, you're not getting a job. Like the employers can suss that out in the interview real quick. They'll understand that you don't understand anything, and then no, those students don't get jobs. And it's important to not listen to them, like, because there are a lot of people complaining that they can't get jobs now. Ask them, try to get the honesty out of them, and ask them if they use ChatGPT or Gemini or whatever to do their assignments, because yeah, they won't get jobs. So be careful who you listen to if you're asking about the job market. There's very different people. I have a really good student, a TA of mine right now, who's got like so many offers on the table. They can absolutely pick and choose where they go and basically choose their salary because they actually know their shit. There's a big difference there. What do you think about cybersecurity? Am I going to be jobless? No. It depends what you want to do. Also, the government is always hiring cybersecurity experts, and they're in need of more cybersecurity experts because that's where like that's where countries are competing against each other right now is with cybersecurity. So if you really know your cybersecurity stuff and you can contribute to that, they're going to hire you. But again, you have to actually know cybersecurity. If you dabble into it and know just surface level stuff, then you know ChatGPT could do everything you could do at that point. But if you really know the hell out of cybersecurity or anything, really, if you know the hell out of it, you're gonna get a job. Cybersecurity, especially because that's where the AI is really failing us right now. There's a lot of really AI slop code out there that's completely insecure, and there are now more data breaches because the AI code is not concerned. It's just concerned about getting things working. It's not doesn't fully grasp the concept of this code has a security flaw in it, and the people who are using AI to write their code for them also don't understand how to spot security issues in that code. So cybersecurity, I think, is a bit of speculation, but I think cybersecurity is going to become a much more important topic as we get more and more insecure code out there in the world, as more and more developers are relying on AI to help them write their code. So I think that's going to be the next spiral is cybersecurity is going to be a big deal. Because these, oh man, when I see students who use AI to write everything, and one, it's cheating, so a lot of times I'm failing them. But the ones that are a little bit borderline, where it's like, I think they used it, but like it's not so egregious that I'm going to fail them. Those ones scare me when they get out there in the world, because they're going to write really terrible, well, they're not going to write code, but they're going to have AI write very terrible, insecure code. And it makes me nervous to use software anymore, knowing how much garbage code is out there. It's actually kind of scary. Okay, so this is our graph class. Our getter, add bidirectional edge. I just went through the whole thing. So let's... that's what I was going to do. I want to look at this in memory again. I want to try, even though I'm going to use a bunch of slides today, which I usually don't do for 11 a.m., I still want to do as much as I can outside of the slides. I think I can explain this one without slides, but after this example, we're going to have to jump to the slides to start talking about this. So I want to introduce a few, let me just expand this whole adjacency list. Oops. And I want to explain a few concepts here. Actually, just one. Is a path in the graph. So a path in a graph is a sequence of nodes where every subsequent pair of nodes in that sequence is connected by an edge. So it's intuitively what you would think of as a path. So like RAND to UCLA to SRI would be a path in the graph, because RAND to UCLA, there's an edge. UCLA to SRI, there's an edge. That's a path in the graph. It's a valid path. But RAND to UCLA, well, I shouldn't go to UCLA because UCLA has connections to everything. Let's start at UCLA. UCLA to Stanford to RAND is not a path in the graph, because from Stanford to RAND, there's no edge there. So that's not a valid path in the graph. Next is distance. The distance between two nodes. I didn't even do length of a path. And the length of the path is the number of edges in that path. So RAND to UCLA to SRI, that would be a path of length 2 because it took me 2 edges. RAND to UCLA to SRI took me 2 jumps to get from RAND to SRI. If 2 nodes are connected by an edge, so RAND to UCLA, they're connected by an edge, so that's just 1 edge, or the number of nodes minus 1, if you want to do it that way, is a distance, I'm mixing up all my stuff, is a path of length 1, and then the distance, I was thinking ahead, the distance between 2 nodes is the length of a shortest path between 2 nodes, and I have to say A instead of the, because there can be multiple shortest paths that are all the same length, and they are the shortest length, but with multiple paths between them. So RAND and UCLA are connected by an edge, so their distance is going to be 1. You're going to travel that edge. That's the fastest you can get from Rand to UCLA. The distance from one node to itself is always 0. You have to travel 0 edges to get there. And then like Rand to UCLA to SRI, there exists a path of length 2. And no matter how much we look at this, we're never going to find a path of length 1. Rand does not have SRI as a neighbor. So we do have to go through at least one other node. Rand to UCLA to SRI does it. That's a path of length 2, and it is a shortest path between those two nodes. So the distance between Rand and SRI is going to be 2. So distance is the length of a shortest path between two nodes. Okay, definitions out. The homework, it asks you to compute the degrees of separation between two actors given an array list of movies. To approach that, first we want to build a graph, which I'll talk about this a bit later, but just to give context to what we're talking about in lecture here, is you're going to build a graph where all the nodes are actors or cast members, and there's an edge between two cast members if they've starred in a movie together. If you build your graph like that, where two actors are connected by an edge if they were in a movie together, then the degrees of separation between two actors is exactly the distance between two nodes in that graph. So what the assignment boils down to is find the distance between these two nodes in the graph that you built. So 1, you have to build the graph, and then 2, find the distance between two nodes in that graph. How are we going to do that? I'm glad you asked. So to do that, we're going to use an algorithm called breadth first search. Now, just like adjacency list and adjacency matrix, there's breadth first search and depth first search, two very similar algorithms. But we're not going to talk about depth first search because it doesn't help us do task 8. We're just going to learn breadth first search and leave depth first search for other classes. You will see that, I'm sure, multiple times in multiple other classes. But breadth first search, we can get this distance information out of, so that's the one we want to use in 116. And what we're going to do is choose some node as a starting node, and then we're going to explore all the neighbors of that node. So we're going to say we start at Rand as the starting node. We're going to explore all of its neighbors. So we're going to explore UCLA, and then we're going to repeat this process. All the nodes that we just explored, we're going to explore the neighbors of that node. So UCLA, we're going to explore all of its neighbors. And at that point, we already explored every single node in the graph. So we're done. This is going to give us a way to visit every single node in the graph, which we had with tree traversals, but we don't have with graphs yet, because there's one big sticking point when running breadth first search, is we have to make sure we don't visit a node more than once. And we're going to do that by checking if the node has already been explored. So when you explore the neighbors of UCLA, we're going to see that Rand has already been explored. So we're going to skip that one and just visit the nodes that have not yet been explored. So that's the base foundation. That's the very short TLDR of breadth first search. And this is where I'm going to have to switch to the slides because it's getting harder to explain this stuff without visuals in my slides. So I am going to switch to the slides to talk about the rest of it, of how we're going to use that breadth first search, that brief description I just gave. Let's give that a more thorough description and talk about how we're actually going to use that to find distances between two nodes in a graph. And then we'll come back to the code and finish up. I'm actually going to, well, we'll save it for when we get there. Okay. And do I still have it open? No, that's the old one. Let's do this. Slides. Yeah, it's sad. Slides in 11 a.m., but it's paths, length of path, distance. I did that, but the rest of it, I'm not good enough to do this in the code. You'll all be completely lost if I try to explain this in the code. And most importantly, implementing breadth first search and finding the distance, like that's what you're asked to do on the homework on task 8. I can't explain this by live coding it without just giving you the homework solution, which then there's nothing left for you to do on the homework on task 8. Because really it is implement breadth first search and use it to find distance, which is what I'll walk you through. I'm going to explain everything you need to do in the slides, and I do hold your hand quite a bit. I basically explain how to write the code, but it is up to you to actually go in and write that code. Game Changer on Fire says, damn. So we're going to run breadth first search here, and this is the full graph visually. And let's run breadth first search and start at Carnegie. And what we're going to do is explore the neighbors of Carnegie, then the neighbors of the neighbors, then the neighbors of the neighbors of the neighbors, and just keep going and going until we've explored all the nodes. So we're going to start at Carnegie and explore its neighbors. And I'm going to keep track of the nodes that I explore and the edges that I use to explore those nodes. So I'm starting at Carnegie, so I'm going to draw that here. And each time I visit a node, I'm going to go lower on the slide here when I visit those nodes. So I'm going to visit the neighbors of Carnegie and draw these lower down to Carnegie and Harvard, and then Case and Harvard. And then Case is going to explore Lincoln. Harvard's going to explore BBN. So I'm going to draw those coming off of these nodes. And then Lincoln and BBN get to fight over MIT, over which one gets to explore it. One of them is going to get there first, and the other one's not going to be able to. Let me just get the visual on there. So I'm going to say Lincoln gets MIT and BBN gets Rand. So Lincoln is going to visit MIT and explore it, add it to this graph, and do all the things and say that it's been explored. Then BBN, I'm going to say BBN gets there second. And when it goes to check MIT, the very important thing about breadth first search is when we check a node, when we check the neighbors of a node, if that neighbor has already been explored, if another node already found it, then we don't do anything. So this edge right here is not used in our breadth first search. BBN doesn't explore MIT, so BBN, this edge from BBN to MIT, we do not use that edge in our breadth first search execution. So BBN does find Rand though, and then MIT finds Utah, Rand finds all three of these. Utah is going to find SRI. Any one of these three nodes could find SRI. I chose Utah for the slides, and UCLA is the only one that can find Stanford. So there's a decent number of edges that we haven't used, that we did not use in this run, that don't show up in this second graph. And the second graph is actually a tree. It's not literally it's weird to say, but if we're coding this up, it'll be in our graph class still, an object of type graph. So it's not like changed into a tree object in our code if we're coding this up, but it is a tree in the sense that it has no cycles. Any graph that has no cycles is theoretically a tree. It is by definition a tree, even if it's not in a tree data structure in our code. So this is a tree because it has no cycles. If we added in any of those edges that we skipped, then this would have a cycle. Every skipped edge would create a cycle in this tree. So these are only the edges we used during breadth first search. We got this tree, and the way we drew it, where every time we find a new node, we go lower on the slide, gives us levels. So if we label the starting node as level 0, and then each time we go down and travel a new edge, we increment the level number by 1. If we do this, then the level number is exactly the distance from the starting node to that node. So from Carnegie, just knowing from breadth first search, the properties of breadth first search, and the way I built this tree, from Carnegie to SRI, the distance is 5, meaning the shortest path from Carnegie to SRI is 5, and no matter how hard you stare at the original graph, you will not find a path from Carnegie to SRI with a length less than 5, because its distance is 5. That's guaranteed by breadth first search. That's how the algorithm is going to work. That's the information that it's going to give us, is the distance information. And this is how we can get our degrees of separation working. So we're going to run breadth first search, keep track of these levels, which I'll just call distance from now on. We're going to keep track of the distance from the starting node to each node, and then take that distance number as our distance. So in our homework, we have two strings that are two cast members, and we want to know their distance in the graph. We're going to choose one of those two as the starting node, run breadth first search, and then look up the distance of the other node. That's our return value, and that's it. That's the crux, the core of what we want to do for task 8, is run breadth first search. Except we have a pretty big problem, is the way I've explained this. So we'll go lower on the slide and just draw our edges lower. How the hell do you code that? Like, you can't code that, right? So let's go through this again. That's just to show that we can get distance information. But let's go through this again and add in some data structures and see how we're actually going to implement this in our code. And this is where this is the most important run of breadth first search. We're doing a couple runs of it here. This is the most important one for task 8. It's the one that walks you through how to do it. That said, if you didn't understand the last one we just did, this one's going to be tough to follow. So they're all important, but this is the one that we've been building up to, is this run right here. Because this is the one where I basically hold your hand and walk you through how to do task 8. And my explanations here, I'm not going to have bullet points. This is one where you do have to watch the lecture and get my narrative where I explain what's going on here. So let's track these, and we're going to use 3 data structures to get the job done here. 3 total data structures. So before you run breadth first search in your code, you're going to be initializing these 3 data structures and setting them up to be able to run breadth first search successfully. So let's go through these 3. First one is a queue. The queue is, my commentary goes away when we start running the algorithm. The queue, I don't care what you used for the queue, as long as you're using the concept of a queue, that you're in queuing and dequeuing, where it's a first in, first out data structure. As long as you have that, that's fine. The easiest way is probably using the queue that we built in lecture, back in the linked list lecture towards the end of it. Using that queue class, except we do need to know if the queue's empty, so adding a method to that class to check if the queue is empty is something you need if you're using that one. Other than that, it's in queue, dequeue, and is empty. Those are the 3 methods that you'll need on your queue class. You can use a linked list or an array list as a queue, or whatever else you want, whatever you want to do, as long as you have the concept of a queue, because the ordering is going to very much so matter. As long as you have that first in, first out type of data structure, that's what we need. As long as you have that, you're going to be good. So we have a queue that's going to track the order in which we're going to visit the nodes, or more specifically, the order in which we're going to visit the neighbors of a node. We're going to need another data structure that marks which nodes have already been explored. On the slide, I'm going to mark them as orange. If they're orange, they've been explored already. If they're blue, they have not been explored yet. In your code, you can use a multitude of different data structures for this. The easiest one is just to use an array list. Just because we've used array list all semester, you know how they work. Whatever data structure you use, you're going to need a way to add values into the data structure and check if the data structure contains specific values. We're going to constantly ask this data structure, has this node been explored before? So in array list, you have .add, you have .contains. You can do it with an array list. Array list is very inefficient. It's going .contains with an array list is an O of n operation, because you have to go index by index. Hey, index 0, do you have this value? Index 1, do you have this value? So on until either you find it or you reach the end of the array list. So there are more efficient options. Going with what we already know, you could use a hash map and map the every node to a Boolean, and that Boolean is either true or false. That would work fine for you, true for explore and false otherwise. Or the one that makes the most sense is probably a set. I would use a hash set for this to track the nodes that have been explored. A hash set works, if you've taken 191, it works just like you expect a set to work, where you throw values into it, it's unordered, and it doesn't allow duplicates. So if you add a value into a set twice, it's going to ignore the second one. It's just going to it's only going to have that value in the set one time, because it's just not going to honor your duplicates. It's not going to allow duplicates. And if you use a hash set, it's O of 1 lookup to check if a value is contained in that set. So it's a very efficient. We're not really concerned about efficiency in 116, but if you want to head start to start thinking about 250, where efficiency is the only thing you talk about all semester, or maybe not the only, but it's the whole theme of the course is how do we use efficient data structures? How do we use data structures efficiently? That's the whole theme of the course. Where we're just trying to write big programs and we don't care if they're slow quite yet. So if you use an array list with O of n, that's fine. As long as you're not testing on the full movies.csv, because your array list will get too slow. It's going to start timing out. In Autolab, I don't test with the full movies.csv specifically for that reason. Anyone using an array list here, it'll time out in Autolab. It'll actually take minutes. Like, I'm not talking about the difference between a millisecond and 10 milliseconds. It'll literally take minutes on certain test cases. Okay, so something of your choice to mark which nodes have already been explored. Something you can ask, has this been explored? And tell it, okay, this one has now been explored. Hash maps O of 1 too, by the way. If you use a hash map of nodes to booleans, that's O of 1 as well. Very efficient. And then finally, a hash map, which is going to store the distances for each node. So for each node in the graph, what's its distance value? This is the one we're really after. This is the information we really want to know. That's going to be in this hash map. And we're going to initialize all three of these data structures with the starting node. So we're going to create all three data structures, our queue, our array list, or whatever else you want to use if you want to use something more efficient, and a hash map. I'll say queue, array list, and hash map because we've talked about all three of those data structures in the course. I don't want to start throwing sets in there. But I wanted to mention that for those of you who do want to think about it in very efficient code, set is the answer here. And we create these three data structures and then initialize them all with our starting node. So we're going to enqueue the starting node. We're going to mark the starting node as explored, so add it to your array list. And we're going to set its distance to 0. The breadth first search is going to give us the distance from the starting node to all nodes in the graph. From the starting node to the starting node, the distance is 0. From a node to itself, distance is 0. So we can initialize, we already know the starting node is going to be distance 0. We don't have to do any work to figure that one out. It's just 0. And for the slide, I'm initializing all of our other nodes to infinity. I'm doing that just so the slide looks better. It just bugs me if our hash map is constantly changing size. But in your code, it's perfectly fine to create a hash map. Only put one key value pair in it. And then as we discover other nodes, then add key value pairs. Put a key value pair in for each node that we explore as we explore it. For the slide, I'm going to use this infinity just to say that we have not yet explored this node. So we don't know anything about its distance. Okay, so that's our setup. We created three data structures, a queue, an array list, and a hash map, and we added our, we enqueued our starting node, we marked our starting node as explored, so added it to our array list, and we added our starting node to our hash map with a distance of 0, so we put the starting node in our hash map with distance 0. That's all the initialization, that's all the setup. So in your degrees of separation, these are some of the first things you should be doing. Create these three data structures, throw your starting node in those three data structures, and then after all of that is set up and you're at this point in your code where all these three data structures are set up with your starting node in them, then we're ready to start the algorithm, the rest of, I mean, we've already started the algorithm, but start the bulk of the algorithm, which actually doesn't take long to explain, but I will go through the full example because it's something that needs a bit of repetition because there's a lot of nuances to it. So what we'll do is, as long as there is something in this queue, we're going to do something, the rest of the algorithm that I'll explain, but we're going to do something as long as there's something in this queue which should sound like we're going to do something while the queue isn't empty. We might want a while loop for that one. So while the queue is not empty, so that means there's something left in there, we're going to execute a loop. So we have our big outer loop, which is a while the queue is not empty. And as soon as that queue is empty, you want to get out of that loop and move on with the algorithm. So while the queue is not empty, we're going to dequeue, take the node at the front of the queue, and check all of its neighbors. For each neighbor of that node, so this is where you're going to get the adjacency list from your graph, get the value at the key for this node, so you're getting an array list of all the neighbors of this node, and then iterating over that array list and checking all of its neighbors. So all the neighbors, in this case, it's Case and Harvard. So we're going to iterate over these nodes, and for each neighbor, we're going to ask, has this neighbor been explored yet? If it has not been explored, which is the situation we're in here, if it has not been explored, we're going to do three things which relate exactly to our three data structures. So with Case, it has not been explored. So we're going to enqueue it. We're going to enqueue it. We're going to mark it as explored, so add it to your array list. And then set its distance equal to the distance of the node that discovered it plus 1. So Carnegie's distance is 0. So we're going to add 1 to that, which is 1. And that's Case's distance. And then same thing for Harvard. Harvard has not been explored. Enqueue it, mark it as explored, set its distance equal to the distance of the node that discovered it plus 1. And that is the algorithm. Like, that's everything you need to know. The rest of what I'll talk about is just reinforcing that and trying to make it make sense. Actually, there's one thing I skipped so far that we're about to hit. So then we do the same thing here and just keep repeating. At this point, we're at the top of the while loop again, and we're going to repeat the process. We're going to dequeue and check all of the neighbors of Case. We're going to check Lincoln. It has not been explored, so we're asking our array list, hey, array list, do you have something called Lincoln? Do you have this node? Have we seen this node before? The array list is going to be like, nah. So we're going to explore this node. We're going to enqueue it. We're going to mark it as explored, and we're going to add its distance to our distance table, or our hash map, as the distance of the node that discovered it, which is Case, which is 1, plus 1, so we get a distance of 2. And the last piece of the algorithm that I haven't explained yet, because this is the first time it comes up, is Case. We're going to get its adjacency list. We're going to get an array list of all of its neighbors. We visited one. Lincoln wasn't explored yet, so we explored it. We did all our stuff for Lincoln. But we're also going to check Carnegie. Carnegie's in Case's array list. It is a neighbor of Case, so it's going to be in that array list. So we're going to check Carnegie. And this is extremely important, is when we check Carnegie, we're going to ask our array list, have I seen this node before? Is this node already explored? And it's going to say, yeah, it's already explored. We've already seen Carnegie. And when we've already seen a node, we're going to do nothing. If one of the neighbors of a node has already been explored, do not do anything with that node. So you have some conditional. If I've seen this node before, if I have not seen this node before, do all this stuff, update my 3 data structures. Else, do nothing. You shouldn't even have an else block. There's nothing to do if you've already explored that node. That's very important, because if you do go back to Carnegie, you're going to end up going infinite. If you don't have that check, you're going to go to Carnegie, enqueue it, update its distance to 2, which is just wrong. Once you add a distance to this hash map, that is the distance. Values will never be updated. These should never change. Once you add a distance here, like Lincoln's distance is 2, we can verify that manually. Distance is definitely 2 from Carnegie to Lincoln. Carnegie to Case is 1, Carnegie to Harvard is 1, Carnegie to Carnegie is 0. All our distances are correct here, and they will never be updated if we're implementing the algorithm properly. They should never be updated, because these are the final answers for these 4 nodes. So we would be updating Carnegie to 2, which would be wrong, And then we're going to eventually DQ Carnegie and then NQ Case again and Harvard again, which will NQ Carnegie again 2 more times. You're going to go infinite. You're going to get stuck in this loop forever. And since we're not using recursion here, it's not going to blow up your stack either. You're just going to have a program that runs forever. So you click run on your test cases, and it just runs and runs and runs and runs and gives you no feedback. Like, it's going to look like nothing's happening. So if you get in that situation, double check the way that you're checking if your nodes have been explored already. Because if it's already explored, you do nothing. Okay, and then we get to Harvard. Harvard is going to find BBN. So we're going to enqueue Harvard, or enqueue BBN, mark BBN as explored, and set BBN's distance to Harvard's distance +1. Then Harvard's going to check Carnegie, see that Carnegie's already been explored, and don't do anything with Carnegie. And we DQ Lincoln. Lincoln is going to find MIT, enqueue it, mark it as explored, set MIT's distance to Lincoln's distance +1. And here's where the tie, I don't think I made a big deal of it in this lecture, but I'll explain it here, is the tie is going to be broken arbitrarily, because either Lincoln could find MIT or BBN could find MIT. Either one of them can, and the tie should be broken arbitrarily. Doesn't matter which one finds it, it's fine. But that doesn't mean you have to do anything in your code. This is just going to come out in the wash. When you run your algorithm, one of them is going to find MIT and one of them's not. And it doesn't matter which one. Since we're only concerned about distances, especially from Carnegie to Case, Lincoln, MIT, that's a path of length 3. Carnegie to Harvard to BBN to MIT, that's a path of length 3. No matter who finds MIT, if it's Lincoln or BBN, it's still going to be a distance of 3. So we're still going to get the right answer. So we don't really care who finds it. It's still going to be a distance of 3. Whenever you have an arbitrary decision like this, that will always be the case. Just based on breadth first search, that will always be the case that the ties won't matter, because it will still, both of them will always be shortest paths, and your distance numbers are always going to be right no matter which one discovers it. If it would matter, then there wouldn't be any choice to make. One of them is going to find it first every single time. That's what breadth first search guarantees for us. And the way that was actually decided, the way it was decided who finds MIT was, well, one, when I made the slide, I just chose. But the way, if this were how it was actually going down, what happened is that Carnegie, I said that its array list, it has Case then Harvard as opposed to Harvard then Case. That means Case was checked first when we visited the neighbors of Carnegie, which means Case got enqueued first, which means Lincoln then got enqueued before BBN, and Lincoln got to MIT before BBN could. So it depended on the order of the array list of Carnegie's neighbors, which depends on the order in which you add the edges to the graph. So that's where the arbitrary decision actually gets made. But again, you don't have to write any special code to say this is how I'm going to handle these arbitrary ties. It just kind of happens. So not something you have to worry about in your code. So BBN, we're going to explore the neighbors. Check MIT. MIT's already been explored. It just got explored, but it's still explored. Like, it's already explored, so we do nothing. Check Harvard, it's already explored, so we do nothing. Check Rand, it's not explored, so we enqueue it, mark it as explored, and set Rand's distance to 3, BBN's distance +1. And notice what's happening with the order of the nodes here. We just visited BBN. We visited Lincoln and BBN, our 2 nodes of distance 2. And after all of the nodes of distance 2, at the front of the queue, we have a node of distance 3. The fact that we're using a queue guarantees that we will visit the nodes exactly in distance order. So we visited all the nodes, the 1 node of distance 0, all the nodes of distance 1 before visiting any nodes of distance 2, or DQing, before DQing any nodes of distance 2. Then we dequeued both nodes of distance 2 before dequeuing any nodes of distance 3. Now we have all the nodes of distance 3. We're going to start enqueuing nodes of distance 4. Then we'll enqueue nodes of distance 5. It will always go in distance order. So that means when we dequeue MIT and find Utah, since MIT has distance 3, if we're dequeuing a node of distance 3, we know that we've already visited the neighbors of every node of distance 2, 1, and 0, any distance less than the node that we're visiting now. And MIT just found Utah, so there's an edge between MIT and Utah. And if we know that there's a path of length 3 from Carnegie to MIT, we didn't remember anything about that path, but we know that we can get from Carnegie to MIT in 3 edges. And we just found a node that we haven't yet explored by an edge from MIT. Then we know that we can get from Carnegie to Utah in 4 edges. Because if we can get from Carnegie to MIT in 3, and we know that that's minimum, we know that's the actual distance between Carnegie and MIT, and we can get to Utah with 1 more edge, we're going to add 1 to that to account for that extra edge, and that's Utah's distance of 4. We know that Utah's distance is 4 at that point. Because if Utah's distance was less than 4, so say Utah's distance were 3, that would mean that Utah would have to be connected via an edge to a node of distance 2. Or else how are you going to have a path of length 3 if it's not connected to an edge, by an edge, to a node of distance 2? That's the only way you can have distance 3. And we've already explored all of the neighbors of all of the nodes with distance 2. So we know that's not the case because Utah wasn't explored yet. So we guarantee that Utah's distance is exactly 4 because we found it through a node of distance 3. And we would have found it sooner if Utah's distance was less than 4. And we know there exists a path of length 4 because we have an edge connecting it to a node of distance 3. So that's kind of the theory behind why this is working, which is more like 250 and 331 style stuff. That's the kind of hand-wavy, high-level proof of why this works the way it works. But it will, if you don't want to think about that, it will, if you follow the steps here of the algorithm, give us the distance from the starting node to every single node. But that's like the why it does it. So let's continue this. Rand, we're going to dequeue. We're going to check BBN. It's already been explored, so we don't do anything. But we do get 3 extra nodes here. So we're going to enqueue them all, mark them all as explored, and set all their distances to Rand's distance plus 1. So they all have distance 4. Then Utah, we're going to dequeue, find SRI, enqueue it, mark it as explored, set its distance equal to 5, our first 5 distance node, which comes after all of the 4 distance nodes. And since we just dequeued a 4 distance node, we know we're not enqueuing any more 4 distance nodes. We're all done with 4s. We have to dequeue these 3, but we're not going to enqueue any more 4s. We know that. Then Utah checks SDC, sees it's already been explored, so it skips it. Checks MIT, it's already been explored, don't do anything. UCLA, we're going to find Stanford. We're going to find Stanford, enqueue it, mark it as explored. It says distance to 5, UCLA's distance plus 1. UCLA checks SRI, already explored, don't do anything, already explored, don't do anything, already explored, don't do anything. And at this point, we can visually see that the algorithm's over. There's nothing else to do. But the way we're writing our code, unless you want to add some extra logic to take care of this, we're writing our code, it will still go until the queue's empty. So it will spin its wheels for a little bit, handling the rest of these nodes, which is perfectly fine. It's honestly not even that inefficient. Is we're going to check UCSB. I guess it depends. It's a loaded statement I said. It's not asymptotically inefficient is what I mean by that. UCSB, we're going to check the neighbors. Already explored, do nothing. Already explored, do nothing. Already explored, do nothing. SDC, already explored, do nothing. Already explored, do nothing. SRI, already explored, do nothing. Stanford, already explored, do nothing. So now the queue's empty. This is when the algorithm finally breaks out of that loop, that while the queue is not empty, that's false. Now we're done with that loop, and we're ready to finish the algorithm. And for our purposes, So right now we have all of the distances from the starting node to any node in the graph. Same information we had in the levels slide, except now we have a way to actually track this information in our code more effectively. And but we have the same information, the level information. And if we're trying to find the distance between two specific nodes, so say our algorithm was, our method call was expected to find the distance between Carnegie and Rand. We started at Carnegie, and then when we're done, we have all the distance information for every node. We're going to go to our hash map, go to Rand, and its value, that's our answer, 3. So the distance from Carnegie to Rand is 3, and we can visually verify it in this example. That's 3 edges to get there, and I'm never going to find a path of length 2 connecting Carnegie and Rand. So that's what you want to code for task 8. That run right there, that is task 8. It's taking my explanation there and turning it into functioning code. That's what you're asked to do for task 8. So if there are any questions on that, because we're going to do one like kind of bonus run of this algorithm, but this is what you need for task 8 right here. You get 2 strings for your 2 actors. Choose one of them as your starting node, run this algorithm, and then look up the other one in your hash map. If it's not in your hash map, that means they're not connected, so you return -1. But if it is in your hash map, you return whatever the value is for that node. Okay. All right, so let's do one bonus one. During the fall and spring semesters, we actually do path finding. So we use breadth first search not just to find the distance between 2 nodes, but find a path, a shortest path between the 2 nodes, which is super fun. I love it, but I think you're all exhausted already. This just doesn't fit in the summer class. It's fun, but we're all exhausted, right? I don't think anyone, well, I think most of you won't complain that you're not doing it. If you are, when the website switches for the fall semester, you can still do the new assignment. You won't have AutoLab if you're not enrolled, but you can still do the other assignment. Instead of tracking the distance numbers for each node, we're going to change just slightly what we're going to track in this hash map. Instead of the distance numbers, we're going to track which node discovered that node. So which node were we exploring the neighbors of when we explored that node? So for the starting node, we have to have some special character, usually null, that says this is the starting character. As long as you're consistent, doesn't really matter what you use. That we're going to have some marker to say this is the starting node. And then for each other node, whenever we explore a node, we keep track of which node discovered it. So Carnegie discovered Harvard and Case. So Carnegie was the node that we came from to get that node to those nodes. And then repeat for the whole thing. Rand was discovered by BBN. MIT was discovered by Lincoln. So MIT was discovered by Lincoln. And track that through the whole algorithm. I'm not going to go step by step and bore you with the repetition again. But in the end, just that one change, instead of distance, track which node discovered each node. And we'll end up with all this information in our hash map instead of distances. And then when we want to find the path, so say we want to find the path from the starting node Carnegie to Stanford, what we're going to do is build that path backwards. We're going to start at our destination. That's the last node in our path. And then we're going to ask that node, which node discovered you? And that's our second to last node. So we can start building our list in reverse. And when we do this on the assignment, it's a linked list, so it's a lot of prepend operations, which are nice and efficient. Stanford is our destination. The one before that is whoever discovered Stanford, UCLA. Then we just repeat this process. UCLA, who discovered you? Rand, that's our next previous node that we can prepend to this list. Rand, who discovered you? BBN, prepend BBN. BBN, who discovered you? Harvard, prepend Harvard. Harvard, who discovered you? Carnegie. Prepend Carnegie. Carnegie, who discovered you? And Carnegie says, no one discovered me. I'm the starting node. I am the beginning of everything. So Carnegie's the starting node, so that means we have our entire path. And now we have our path, a shortest path, which in this case is the shortest path. There's only one from Carnegie to Stanford. We have the shortest path from Carnegie to Stanford by just changing slightly what we store in this hash map, and then doing a little extra work at the end to actually build our shortest path. Then in the other semester, this is a screenshot of the game that they build, with the game engine and everything, the big project that they do in the fall and spring. And they're given this game, which is a top-down tile-based game, and they need to find the path for their enemy AI. Like this enemy right here needs to be able to attack the player. It's going to hunt down the player, but we don't want this enemy to get stuck on this wall right here. Because if you're just saying, okay, create a vector from here to here and just travel that path, it's going to go right here, get stuck on this wall, and just not be able to get to the player. And then it's not going to be a very compelling game. The AI isn't advanced enough to be interesting to be able to compete with the player or anything. So we want more advanced AI. What we want is the AI to be able to avoid these walls and go around, know to go around to be able to get to the player. So to do that, we're going to build a graph where each tile in the game where the AI is allowed to move to, we're going to create a node and then create edges between those nodes if it's a valid movement of that AI. So these are all of the possible movements that an AI can take in the entire level. Then the AI is going to know its starting point or its starting node and its destination, run breadth first search, and find that path from itself to the player. So when we're playing the game, we see this, but our AI characters, they're actually just seeing this. They're seeing the graph. And then they're going to use that graph to run breadth first search from their starting point to the end point and get a shortest path. There are a lot of shortest paths. They can go this way, this way, this way, and then over here, a lot of choices as well. When do they take that move to the left? A lot of different paths, but here's a shortest path that the AI can find, and that's the path it'll traverse to get to the player with the least amount of moves without getting stuck on walls. Then the AI is going to travel that path and attack that player. If that player doesn't move, they're going to get attacked by the AI. And that's it for slides forever. For me, until fall. Okay, so let's jump back to the code. And where are we on time? 12, 11, 12, 1. We go to 1:30, right? Oh, we got tons of time. It's possible I'll end early here too. If anybody has questions, if you want to see anything, get your questions ready because I think we will have a little time. We had a little time at the end of the first one. No one had questions, so I ended like 25 minutes early, I think. This one usually takes longer doing all live coding. I had to build the whole graph class and everything, but we're still doing really good on time. So what I want to do here is what's already in the repo. It'll look a little different because I don't remember exactly what I have here, but this is already in the repo, the movie graph class, and that'll be in the repo after I code this. I won't push the new code as usual. I won't push the new code in there, but you have movie graph already. And I am going to intentionally deviate already because I'm going to create a movie class. And let's start task 8. I mean, it's already in the repo, so you already have it. But let's live code the start of task 8. I want to do creating the graph. I haven't talked about creating that graph at all yet. And what we want to do, I'm going to use the same test that I created in the... You know what? No, I'm not going to do that. I'm going to recreate it. We have all the movie data from our movies.csv, which you're familiar with from task 6. And we want to take all this movie data and create our graph. So we have all of our movies, and what we want to do is for each movie, for every single movie in here, we want to take every pair of actors or cast members and create an edge between them in the same way that we created our graph for the early days of the internet there. So we need an edge between Tom Hanks and Tim Allen, Tom Hanks and Don Rickles, Tim Allen and Don Rickles, etc. Every pair of actors should have an edge connecting them. That's our goal. I feel like I got extra crap here. Let's get rid of those. This movie graph and move. Oh, I did delete movie. And let's get the easy one out of the way. Actually, no. Let's set this up so you have something to mull over, so you see where we're headed with this. Main. Well, I set up the movie class because the movie class I just got to recreate part of the movie. Someone's asking about the final right now. You could just ask in lecture. So I want to be able to take all that movie data, which I am going to start as a file. In the code, your degrees of separation class constructor takes an array list of movies. So you don't have to mess with file IO if you don't want to for task 8. It is optional. You can create your array list manually. That's perfectly fine. For this example, I'm going to start with the file name, though, and do the whole shebang. So file name equals movie test 1.csv. I'm not going to make full test cases, but I am setting up a test file. So we want to read this file that we're going to set up right now, because this is a lot of information. I'm not going to get any good test cases out of this because there's just too much information here. I shouldn't say never. If there's a known quantity in here, like for example, the test cases that I give you in the homework description, then you can use those as some test cases, but it's really hard to verify any other test cases. How are you going to verify the degrees of separation between any two actors in all of this mess? So you want to do the same thing that we did before. Let's pick on Edward Norton here. Let's grab just a subset of these movies. Oh, rounders. Let's do rounders. And Fight Club. Good movies. And just like in task 6, I want to cut these down a bit. 3, my eyes are bugging. Just because that's too much information. I don't want to mess with this large of a cast list. So let's cut this down quite a bit. I want to keep Edward Norton because I want at least one actor who's in both movies. And get rid of all the rest. So sorry to all the talent that I'm deleting here. I just don't need you for this test case. And use this as my testing file. So it's very trimmed down. I know exactly what to expect out of this data instead of using the full movies.csv. Okay, so with that test file, I want first I'm going to have to read movies, which is going to be just like your array list of movie, which is going to be just like your task 6 read movies method, which I honestly forgot about. But one of the task 6 methods is, oh no, it's not exactly though. Very similar to this though, is your read movies method. I guess that is quite a bit different. So I didn't fully spoil it, but I'm about to anyway. So read movies, which is going to take a file name. and create an array list of movies. Movies equals new array list. Return movies. I'm not going to implement the method yet. I just want to set this up first. And then the big method that we're after, which is going to create a graph. Week 12 lecture. Yes, the one that I just created. A graph of strings. So our actors are going to be strings. And I want to create a graph where all the nodes are actors and there's an edge between two actors if they've starred in a movie together. That's the graph that we're after. That's the graph that exactly matches distance between two nodes is exactly degrees of separation. And then at that point you take it over from what I just covered in the slides. But the homework is in two halves. Create the graph and then run breadth first search to find distance in that graph. So here's the creating the graph part is graph generate graph, which takes an array list of movies, which is your degrees of separation constructor. It's recommended that you create your graph in the constructor and then use the same graph each time degrees of separation is called, just because it's more efficient. Though I do see students creating the graph in the degrees of separation method, which is fine, I guess, but it just bugs me because it's horribly inefficient to recreate the same graph every single time. So generate graph movies, and we're going to need a graph of strings. Graph equals new graph, and return graph. Okay, so there's our setup. That's what we want to do. Oh, that's not our whole setup. Our graph of strings, graph equals generate graph. I didn't make these static. Static. I forgot that in the other lecture too. I'll just always forget that. That's not something I can forget forever because I'll just get errors and know what the error is. Generate graph of read movies of file name. And then just some lines so I can set a breakpoint for later on. Okay, so that's what we want to do. Let me set up my movie class. While you think about that a bit, private string title, private array list of strings, array list of string cast, a public constructor. I'm just going to do a subset of the movie class. I'm not going to set up inherits with rateables and everything. Just the bare minimum of what we'll need. So a movie constructor that takes both of these: title, array list of string cast, this dot, oh my goodness, this dot title equals title, this dot cast equals cast. Public string get title, return this dot title, public array list of string get cast, return this dot cast. All right, we got a movie class. Okay. So let's read these movies. I'll try to do things a little different than I did in the test 6 examples, the lecture 6, the files lecture. Do things a little different just to, I don't know, keep it spicy, keep you something interesting happening, but not too different. But let's read the lines of these files. So we have files dot read all lines, paths dot get file name, and instead of going through, instead of what we did was stuff this into an array list and then iterate it over the array list, we can actually do this all in one line and just iterate over whatever read all lines gives us. It's a little bit cleaner, a little bit, I mean, I guess it's a matter of taste, whether you like this better or not. But I don't have to care what this returns as long as it returns something that's iterable, which it does. It returns a list, which it actually, I'm pretty sure it does return an array list, but it returns it as a list interface. So this, I don't have to think about any of that. I'm just going to iterate over it directly. And then I'm going to get my try catch block. So try to do this, but catch the IO exception. The IO exception. And I actually don't have to do anything. If there's an IO exception, who cares? I'm just going to return movies. So I'm initializing movies to an empty array list. So if there's an exception here and I can't read any of the data, I'm just going to return movies, which is an empty array list. So I'm getting the behavior I want without needing the catch block to do anything. And then for each line, I'm going to do my splits. I am still going to use an array list here. String, array list of strings. My splits equals line dot split on comma. Arrays dot as list. New array list. So I get my, So I get my splits, and then the title, string title equals splits dot get 0. And then splits, I'm going to remove the value at index 0. And then my movie equals new movie of title. And I'm just going to reuse the array list for splits and compact this code pretty well. So I'm getting the value index 0, removing the value index 0. Everything else on the line is cast members. So if I remove the title, everything left in splits is the cast list. I could do this with the one extra line I did in the other lecture where I said array list of strings cast list equals splits, but it is a redundant line, and even IntelliJ was yelling at me. Just like it's yelling at me about these two, but it can deal with that. Because there's get first and remove first. Get first, remove first. It wants me to use those methods, but I'd rather put the index there. I don't know, I like it with the index. I think it's more clear. I don't need a special method to get the first value. And then movies dot add movie. Okay. And when we return this, let's run the debugger and make sure we're not doing full proper testing here. But we still want sanity checks. Oh, and it looks like we failed our sanity check. So we're returning an empty array list of movies. So let's see what we did wrong. Movie test1.csv, movie test1.csv. Oh man, I actually got some debugging to do. File name movie test1, movie test1. Well, we get a debugging tutorial. Sweet. I ain't complaining. So we're going to go into read movies. Let's figure out what happened. I like when I have legitimate mistakes because you get to see my actual debug process instead of some pre-canned lecture example that I prepared. So we're creating movies as an empty array list. We're going to read the files. The one big thing could be if this file doesn't exist. Oh, I see it now. I see what the issue is. This file doesn't exist. So we're going to get into this. Read all lines does its thing. And we go right to return movies. And if we add something here to indicate error, and we run this code, we're actually going to get that error. That file doesn't exist. File doesn't exist. Of course it doesn't exist. So movie test1.csv does not exist. So all our paths start at the root directory. So we're looking in this directory for a file named movie test 1, and we're not going to find it. File not found. What I forgot was data slash. So we go into data slash movie test1.csv. Now we're going to find that movie. So let's get rid of our breakpoint. Let's keep our breakpoint here and see if we do get our data. And movies, we have 2 movies. And I want to make sure I get all the right data. So I'm going to double check this one too. Cities, we're not doing cities, we're doing movies. And we have Rounders with 3 Matt Damon, Edward Norton, and John Malkovich. And Matt Damon, Edward Norton, John Malkovich. So we got that. And Fight Club, Edward Norton, Brad Pitt, Meatloaf, and Jared Leto. Got all our cast members, all of our information. And especially when I'm removing the value at index 0, I want to make sure I did that right. Make sure I don't have like Fight Club as a cast member. And I want to make sure I didn't remove the first cast member. Edward Norton and Matt Damon better still be in there. Of course, we would formalize that with actual test cases, given more time and if we're writing production code. But for our purposes in the middle of a lecture, I'm going to be satisfied with that. That's fine testing. Doing the good old-fashioned print to the screen and manually check with my eyeballs. I'm going to live with that for this example. It's not good if the program gets large programs, like we write in 116, but for this one, we'll be fine with it. Okay. So now generate graph is getting that array list of movies that we read from our file, and we want to generate a graph from that. And I'm going to do this in a weird way first, the way that I see most students doing it when you have to do this on your own, which is fine. I'll just do it and explain. But it is fine for our very specific application that we're using. But we want to iterate over all the movies. So for movie in movies, and then iterate over the cast list for this movie for string cast member 1 in movie.getCast. So we want to iterate over every pair of cast members. So it makes intuitive sense that I want to iterate over all the cast members, then iterate over all the cast members. And then go to my graph and add a bidirectional edge, cast member 1, cast member 2. I think that makes intuitive sense. That's how you would build your graph. And it's pretty simple, pretty straightforward too. There's your graph. Every pair of cast members for every movie is in this graph. So if they were in a movie together, they will be in this graph together. Let's set our breakpoint on this empty print line that I added just for my breakpoint. Run this and see what graph we actually get. I don't want cities tests. Why do I have so much extra stuff? Did I click that? Oh, I think I clicked it to check something. So let's see if we have our graph looking the way we want it to. So adjacency list, we have 6 different actors here. So we have 6 keys. That looks good. We have all of our 6 actors as keys in our adjacency list. So this is checking out. So far, so good. And let's take a look at Matt Damon. Already we see an issue. There's 6 neighbors. So Matt Damon, where is he? Has Edward Norton and John Malkovich. Those are the only 2 neighbors we expect from Matt Damon because it's the only 2 actors he's been in a movie with. But if we expand this, we're going to see some issues here. We are going to see Edward Norton and John Malkovich, but they're all duplicated twice here. And Matt Damon has himself as a neighbor twice. This is because when we went through the array list, we're going through every array list. We're going through the whole array list and the whole array list for each value in that array list. So we're going to go through Matt Damon with Matt Damon and Edward Norton and John Malkovich. We're going to go Edward Norton to Matt Damon, Edward Norton to Edward Norton, Edward Norton to John Malkovich. We're going to repeat a lot of the information. We're going to get a lot of duplicate extra information here. Now this is actually fine. It's not fine, but we get away with it with breadth first search, because when we go through the neighbors of Matt Damon and we're going to explore his neighbors, we're going to explore Matt Damon. Well, if we're exploring the neighbors of Matt Damon's already been explored, so we ignore it and do nothing. Then we get to Matt Damon again, already explored, ignore it, do nothing. Edward Norton, process Edward Norton, mark him as explored if he hasn't been already, same with John Malkovich. Then we get to Edward Norton again. No matter what happened here, he's definitely already been explored here, so we ignore it and do nothing. And same with John Malkovich, we already seen him, ignore, do nothing. So because our algorithm is going to ignore anything that we've already seen once, we actually get away with this, and it's fine-ish. You know, it bugs me, but you would get credit on the assignment if you do this. And so you get away with it, but with bad practice. But I want to fix this. Let's fix this and do this in a smarter, I shouldn't say smarter, but in a more efficient way. So instead of iterating over the cast members directly, I'm going to iterate over the indices. This is one situation where we want the indices and not the values directly. So we have to go back to our original for loop of actually iterating over indices like this. So int I equals 0, I less than movie.getCast.getSize, I plus plus. And then I'm going to get cast member 1. So string cast member 1 equals movie.getCast.getI. Because what I want to do, let me explain what I want to do, is for each value in this array list, I want to iterate over all of the rest of the values. So when I'm going Matt Damon at index 0, I want to iterate over index 1 and 2. Then when I get to Edward Norton, I want to iterate over just index 2, because I've already done Edward Norton to Matt Damon. I only need Edward Norton to John Malkovich then. So Edward Norton, iterate over these 3. When we get to Brad Pitt, we've already done Brad Pitt and Edward Norton. So we just need to do these 2. And when we get to Meatloaf, we've already done Meatloaf and Edward Norton and Meatloaf and Brad Pitt. So we just need to do Jared Leto. So we want to do everything after that index. So we're going to set up our second loop with another iteration variable, int j equals 0, j less than movie.getCast.size. And oops, I already messed this up. I did that. All that build up and messed up the punchline. J, we're going to start at I plus 1, the index after the first cast member that we're looking at. So if we're looking at cast member 1 at index I, we want to go iterate over all of the indices after that cast member. So start at I plus 1 to the end of the array list and get cast member 2 at index J. So cast member 2 equals movie.getCast getCast.getJ. And with that change, our graph's going to be a lot cleaner. So Brad Pitt was in a movie with Edward Norton, Meatloaf, Jared Leto. Edward Norton, Meatloaf, Jared Leto. John Malkovich, Edward Norton and Matt Damon. Matt Damon, Edward Norton, John Malkovich, Jared Leto, Edward Norton, Brad Pitt, Meatloaf, you get the idea. And then Edward Norton, who's been in both movies, he's our one common thread between them, should have everybody else listed as a neighbor. He's been in movies with all of the other actors, and we see that he doesn't have himself in here either. So we cleaned up our data structure, got rid of all that duplicate data, have a nice clean graph to work with. Which once we have this graph, this is where it's handed off to the slides where we did that whole breadth first search, 3 data structures, while the queue's not empty, etc. This is the graph that we want to work with for that. Now this isn't 100% what you want to do, because you're not in a static method, you're going to be in a constructor. But it's the exact logic that I pretty much, I mean, I just did part of the assignment for you, but literally, no, can't say that. But with very minimal changes, you can integrate this into your assignment. And I don't want to hear anyone complain about that, because I could have just done nothing here. Oh, instead of starting the assignment for you. Yeah, I did still leave a few things for you to do. I didn't put it in a degree of separation class, for example. Okay. And that's the end of the content I wanted to cover. Oh man, we are still early. All right, till 1:30, and at 25 minutes early in the other lecture. How did we end even earlier here with live coding? Well, if anybody has questions, now's the time. The last lecture time. Last time aside from office hours. I'll definitely hold my office hours this week still. I'm going to play it by ear for next week. I'm going to take a look at how the submissions are going, how the Piazza posts are going, and play it by ear. If there's going to be demand, I'll be there. But if there's going to be demand from a bunch of students who started at the last second, I don't know. Because the semester's over. After this week, the semester's over. Like, the fact that the final deadlines aren't all this Friday is giving you extra time to have that one last chance to pass the class. And that doesn't necessarily mean you're going to get support during that extra week. So I feel no obligation to hold office hours, but if I feel like I can help somebody who's been trying, I'll hold office hours. Either way, me and the TAs will still be watching Piazza, so we'll at least be there. So, does anyone have questions? Anything else you want to see from me before the lecture's over and the semester's over? I assumed you would have asked by now. I gave a bit of time there. Because if not, those of you taking the final, good luck on it. For the final exam, if you don't need the final, I won't even send you an email for it. I might send out emails before, like either today or tomorrow. I might send out emails that just say, this is to confirm that you don't have to take the final exam. I know some students stress. Actually, I probably won't. Nobody's been asking questions about that. If a bunch of questions pop up on Piazza, maybe I'll do a blanket, just email everyone. But if you are unsure, if you send me an email, I'll check your status and then confirm with you directly. Now that I think about it, I'm not going to send a mass email. Mass emails are just annoying. It can be clutter. Especially if you know you don't have to take the exam and you see an email from me that says final exam information, you're going to have that moment of panic that's like, oh shit, do I have to take that? So I don't really want to do that. But if you are taking the final, those of you who do have to take it, when I do send the email for the final exam, if you only need like OOP but not data structures, I'm only going to send you the 2 OOP links, and vice versa. If you only need data structures, I'll only send you the 2 data structures links. And if you need if you need both, then I'll send you all 4 links. Is the difficulty for tracing the same on the final? Yeah, the final is going to feel very much so like the midterm. It's going to be the same level of difficulty, same concepts are being assessed. If you study your midterm and you understand all the mistakes you made on the midterm, you're going to do well on the final. So if you have to take the final, good luck. Good luck wrapping up the rest of the tests. I'll be on Piazza. I'll have a few more office hours this week for sure. Today and Tuesday, I'll still hold my office hours for sure. And if you're done with everything, have a great summer. Enjoy your summer. Yeah, I don't see any questions. I answered the one about the final. All right, and that's it for me. Last stream. Take care, everyone.